Hi there. This video is on section 2.3, using equations to find two-sided and one-sided limits. So in the previous video, what we did is we found some limits using tables and graphs. So now we're going to be using equations themselves to try to find. Now, this can be very difficult with some equations, so I'm going to be using some simple equations right here in chapter 2, but we can get more complicated equations as we get more tools to use in the calculus class. So these are the examples I did previously. I actually forgot to write down the limits for g and h. That was the sine function. And when we looked at what happened when x was close to 0, we found that the y value was getting close to 2. So that limit as x approaches 0 will have a y value of approaching 2. So this limit right here is equal to 2. And when we looked at infinity, or at least going towards infinity, when x was getting larger and larger and larger, we got the y value getting closer and closer to 0. So I neglected to write down the answers to g and h. I just said them orally. So for completion, those are the answers for g and h. All right, so how do we do some of these things using equations? Well, I did promise in that previous video that I would revisit example C and do that using an equation. All right, so example C, make this a little bit bigger, has the limit as x approaches -3, and it has this fraction thing. So I'm going to rewrite the problem over here. Limit as x approaches -3, and I have this squared thing on the top, and I have this on the bottom. All right, hopefully you can read that well enough. Try to clean it up. All right, well, without a lot of sophisticated calculus tools, we're going to have to rely on our algebra to try to figure out what this limit's going to equal to. Well, we do know algebra with squares. We can factor, we can complete the square. We can do other things with x squared types of equations that we learned in our pre-calculus class. Okay, so I'm going to keep writing this limit thing. The top part is an x squared function. I'm going to factor it. This one I made to be able to be factored. Not all x squared equations can be factored. So we're going to do a factorization. We have an x and an x. We need two numbers that multiply to be -3, and somehow everything combines together to give us a +2. With a little bit of trial and error, you'll find that +3 and -1 are numbers that will actually correctly multiply to give you x squared plus 2x minus 3. So that's the factorization of the top. On the bottom, I would do the same thing. I would try to find out factors that multiply. In this case, I need two things to multiply to be x squared. I need two things that multiply to be -9. And since there's no x term, sometimes somehow they have to combine together to give me 0 x's. And so what happens there is a +3 and a -3 will work just fine. Again, you should verify that when you multiply out these two binomials, you recover or recreate the x squared minus 9 to verify that it's actually correct. Now, no matter what x value we choose, I mean, we're choosing x values close to -3, like -2.9 or -3.1. This thing right here, whatever that number +3 and the number +3 right here, they will be the same, and they will divide to equal 1, or some people like to say cancel. Okay, so no matter what, when we have values of x that are close to -3, or any value of x that's not exactly -3, these two will divide out to equal 1. And so what we're left with is x minus 1, x minus 3. And we can actually graph this function separately, and we can notice it's a continuous function. We can even find out what happens at -3 by substituting in the -3 value. This only works for continuous functions. So we have to verify this is continuous function. So I can graph the function x minus 1 over x minus 3. Let me do that real fast. Y equals x minus 3, oops, x minus 1 over x minus 3. Did I remember that correctly? Let me go back and check. X minus 1, x minus 3. I'm trying to find out what happens when x is close to negative 3. All right, so even though this is one of those hyperbola problems, I'm really only concerned what happens when x is close to negative 3. So there's negative 3, and you can see the function is continuous, right? It goes straight across here. It even has a value at negative 3, which is, drumroll please, indeterminate from the graph, because I can't. Oh, there it is, negative 3 and then 0.667. But once again, we could just use the equation because we know we can plug in negative 3 into the equation. So here's my equation. I'm going to be plugging in the value of negative 3. And that gives me negative 3 plus 1, or excuse me, negative 3 minus 1, and then negative 3 minus 3. Notice I'm not writing the limit anymore because I'm actually finding out what happens when x is negative 3. So I don't write the limit anymore because I actually plugged in the negative 3. Negative 3 minus 1 is negative 4. Negative 3 minus negative 3 is negative 6. And negative 4 over negative 6 can be simplified, rewritten as 2/3. 2/3 is that 0.666 repeating number that we saw from the previous video. As a decimal, we thought it might be 2/3. And in fact, using the equation, we know it is in fact exactly 2/3. All right, so we're going to have to rely on some of our algebra to simplify these things. But soon we're going to be developing some other tools to help us determine limits using the equation itself. The most powerful tool will be called L'Hopital's rule. Strange little name, perhaps, if you've never heard it before. But we'll be crossing that bridge when we get to it. Right now, we're just trying to understand these limits without getting all of the fancy formulas in the way. All right, so let me give you some sort of general understanding of limits, two-sided limits, one-sided limits, some edge cases, some other things, and that'll be it for our video for today. So here's some pictures here, and I just wanted to remind folks for these pictures that when we're trying to find limits, we're trying to find what happens when x is very, very close to a number. All right, so let me zoom in just a little bit more. Okay, so for this first graph on the left here, I'm trying to find out when x gets close and close and closer to a. And you can see right here that the y value is L. So the limit as x approaches a, as x gets infinitesimally close to a, of this function, whatever this function is equal to L. That's the y value. Let's see if I can change this thickness here. No, that's pretty much what I'm stuck with. Okay, that's the y value when x is very, very close to a. In the second example, example B, right over here, there's the a again, and the graph has a dot right here. So that's where the graph is. It's x is a and y is definitely not L. It's definitely some y value lower than L. So what's going up there? Well, again, I'm not sure what the resolution is for you, but that's an open circle. That's an open circle there saying that the graph is not continuous there. It jumps from there to there. However, the limit doesn't say what happens exactly at A, even in this very strange situation where what happens is actually down here. When x is very, very close to A, we're looking at values right here. They get closer and closer. The y values are getting closer and closer to L. And that happens from the left side and from the right side. As I choose values of x getting closer and closer to A, the y value gets closer and closer to L. So even in the strange case right here, we say the limit as x approaches A of this function is equal to L. All right, and this third example, again, if you have an open circle, don't let that worry you. There's an open circle there. But again, we're going to say that this limit is equal to L, this limit as x approaches a of the function is equal to L, because you can see from the picture, let me move me over there a little bit. Oops. If you choose values that are slightly larger than a, the y value is getting closer and closer to L. If you choose x values that are slightly smaller than a, but getting closer and closer and closer to a, right? These are x values getting closer and closer to a, the y values are getting closer and closer to L. So a lot of times people get confused about continuous or open or closed circles, things like that, and make mistakes when trying to find limit answers. It just happens when x is very, very close to 0. Okay. By the way, let me use the language I used from before. In example A, this is a continuous graph. It goes continuously without any breaks. There's no open circle on this particular problem. And so you could actually plug in A directly into the equation if you had it, and that would give you the value of the limit. All right, let me zoom out here. So I have an example here of a graph of the function gx. I'm not going to give you the equation right now. I'm not worried about equations as much as trying to help people understand limits. We talked about one-sided limits and two-sided limits. So the limit as x approaches 2 with a little plus sign here means we're only considering values of x which are larger than 2, right? So this is x is larger than 2. Instead of saying larger than 2, I'm going to use a math symbol. I hope you don't mind. Greater than 2. All right. So those are values to the right of 2. And so looking at the picture, here's 2. If I only choose x values that are larger than 2, the y value is getting closer and closer to 1. So we would say this is equal to 1. And I can write down the same problem, but instead of using a plus sign, I can use a minus sign. That was supposed to be a plus sign up there. I don't know if that's clear. Sorry, let me just try to fix it. When I fix it, I'll probably make it worse. But it's supposed to be a plus sign up here in case someone looks at this and tries to figure out what's going on. So the minus sign, that means we're using values that are smaller than 2. So we would say x is less than 2. And on the picture, we would be choosing values of x which are less than 2. So the values of x that are less than 2 are values like 1.9, things like that, over here to the left of 2. Remember that we do have to use the function to find y values. So when x is smaller than 2, we're up here on the function. The function is this thing over here. So here's like 1.9, 1.99, 1.99, all the values of x, which are getting closer and closer and closer to 2, but less than 2. The y value appears to be getting closer and closer to 3. So we would say the limit is equal to 3. And lastly, if I talk about the limit as x approaches 5 of this function, whoops, I forgot the actual function. I'm supposed to write down the limit of what? This is the limit of the function. The function is gx. That's what it specifies here, gx. So if I'm coming from the right, the limit as x approaches 2 of g of x is equal to 1. And coming from the left, it was equal to 3. And I can get 5 from both directions. There's no plus sign or minus sign here. So for the limit as x approaches 5 of this function, I would have to go from the left and from the right, and they would have to agree. So from the left-hand side, these are values of x which are slightly smaller than 5. It appears that the y value is getting closer and closer to 2. And if I choose values of x which are greater than 5 and getting closer and closer and closer to 5, again, it appears that the y value is getting closer and closer to 2. So this answer is 2. And if you're wondering about this dot, remember that is the actual value at 5. So the value of g of 5 looks to be a little bit bigger than 1, maybe 1 or 1.5 or something like that. But that doesn't answer the question of what is the limit as x gets very, very close to 5. Okay, so in this case, it's not continuous, so we can't find it directly, but we can find it by getting very, very close to 5, in this case on both sides. Okay, so those are those examples. And then here's another example down here where I have a graph that wiggles like this. You may see a couple wiggling graphs like this in the homework. One of the other things I wanted to show you is that We can do more complicated types of equations. Like in my example for L here, I have x times g of x. That would be the same thing as x is approaching 5 for this first thing, and x approaching 5 for the second thing. So the way we write this is the limit as x approaches 5 of the first part, x, times the limit as x approaches 5 of the second part, g of x. There's no necessity of trying to do everything at once. You are only trying to find out when x is very, very close to 5. So you can find out when x is close to 5 and then multiply it times g of x when x is close to 5. Right? Oh, this is hx function. I think I got things a little confused. Anyway, let's go back up to the gx function up here. We know that as x approaches 5, the gx function is getting closer and closer to 2. So we know that this is going to be equal to, well, as x approaches 5, that becomes closer and closer to 5. And as x approaches 5, the g of x comes closer and closer to 2. So we get 5 times 2 is 10. And likewise, if I have g of x squared, when x is getting closer and closer and closer to 3, remember, x is the only thing that's getting closer to anything. So that x value right there is getting closer and closer and closer to -3. So we can do this. We can just find out the limit as x approaches -3. And we could find out what happens when we plug in the -3 directly into this. So we would do g of x, and then all of this we could square. The squaring function doesn't impact x, or x doesn't impact the squaring function. So we can do that at the end. We don't need to do it all at once. But of course, it affects the gx function, so we have to do that there. So we have to find the limit as x approaches -3 of the gx function. We don't have it here because I don't have any x values around -3. I think I meant this to be the hx function. I just mistyped it. So if I was doing the hx function and sort of edit this on the spot, let's say it's hx function. These are both supposed to be hx functions, and I just typed them. I think it's copy paste error. Sorry. All right. So if it's the hx function, then I would do the limit as x approaches 5 of x times the limit as x approaches 5 of the hx function. And I could find out what happens at 5 for the hx function. And likewise, I would do this for the hx function. So we can do it for whichever function if we have the information for it. Let's do the second one, m, first. So as x approaches -3, what is the value of hx? Well, here's -3 right here. And here's where the function has an open circle at -3, but we're only trying to get very close to -3. So if you choose numbers that are smaller than -3 or larger than -3, the y value gets closer and closer to whatever this is. So let's say it's counting by, ones, 1, 2, 3, 4. I don't have a scale here. Another gym fail. But if I scale by ones, then this value would be 4 squared, or 16. And back to letter L, or example L, if I'm using the hx function instead of the gx function, I would have x approaching 5 of the x part, this first part right here, and then x approaching 5 of the h of x function, that part right there. Well, we know x is 5 when x is very, very close to 5. What about for the h function? Well, 5 is right here. And I don't know what that is. I mean, I know, I know that looking at it from the right-hand side, numbers of x that are larger than 5, it appears to be getting closer and closer to a y value of 3, right? We can see these numbers for y get closer and closer to 3. But on the left-hand side, it's wiggling up and down. It's wiggling so fast up and down that I can barely see anything in this graph. This graph is just going crazy up and down. So I'm not sure if it gets closer to 3 or closer to some other number, or I don't know, whatever, no number at all. And limits have to agree on both sides in order for the limit to exist. If we're doing a two-sided limit, a normal limit, the two sides have to agree. This right here is a two-sided limit. X approaches 5. So because the hx function doesn't agree on the right left, the right side says it's 3, left side says I'm not really sure what it is, then we would say this thing is not existing or do not exist. Does not exist. All right, so those are some more esoteric examples of things to watch out for that you might see in the homework. I'll give you a couple last examples of problems here. Let me zoom a little bit. You might see, or you might see in the textbook, or you might hear a person say that limits are well behaved. In the textbook, they call them the limit laws. Basically, you can do things separately. So if I have the limit of x cubed minus x squared plus 5, I can just compute the limit of each particular part. I can do the x squared, the x cubed part separately. And then I can just subtract off the x squared part because nothing really influences anything else, right? They're not connected. They're just added or subtracted or multiplied or divided. So this is what we mean by well-behaved. You can do them separately as long as you can separate them with operations. Likewise, for letter O, really the only thing that's moving here is x. The ln is not a moving function. I mean, it takes different values for different values of the inputs, but x doesn't affect ln. The only thing I'm going to be doing is putting x in for here. So the way we can write this is the natural log of the cosine of the limit as x approaches 0 of x. So you don't have to get wrapped up with all the complexity of a function if you can find out where you can find out what the x is. Now, for these particular problems, this is a continuous function. So if they're continuous, you can try substituting the value of x. So for this one, x approaches 2 of x cubed. That would be 2 cubed. And x approaches 2 of 2 squared, or x squared would be 2 squared. And x approaches 2 of 5. Now you got to be careful here. There's no place to plug x in, right? This is just the function 5. So this is just 5, right? It just says 5, not 5 plus x, not 5 times x. It's just 5. So no matter what x is to, the function is 5. So we can just compute these directly and get the limit by plugging things into the continuous function. 8 minus 4 is 4 plus 5 is 9. And likewise, the natural log of the cosine of x is a continuous function. So we can plug in 0 here directly. Whoops, it's supposed to be a different color. We can plug in 0 here directly. Well, what happens to the number x when x is very, very close to 0? Well, it becomes 0, right? So when x is very, very close to 0, then x is indistinguishable from 0. So ln of the cosine of 0. So if you remember your trigonometry, the cosine is the x value on a unit circle with this, angle measurement. So the angle measurement of 0 means we're right on the x-axis. So the cosine of 0 is equal to 1. And if you remember your logarithms and exponentials from your algebra and precalculus courses, the natural log of 1 says, what's the exponent on e that gives a value of 1? And the answer is 0. I'll just write here a little because e to the 0 is equal to 1. Right? Any base number raised to the 0 exponent is equal to 1. So we have the natural log is equal to 0 there. And for years and years and years, people told you, you can't divide by 0, you can't divide by 0, run away, hide in the sand, whatever you want to do. And you really can't divide by 0. I'm not going to change that fact. That is a fact. But we shouldn't be so afraid of 0, right? So I have some examples here where you shouldn't be afraid of 0 too much. We should investigate. It should be something in which we don't know what is ahead of time, but we should be able to investigate it. So what happens about 6 divided by x when x is close to 0? Right? Infinitesimally close to 0. right? That was essentially going to find out what happens as 6 divided by 0. Well, we can use our graphing calculator to do 6 divided by 0. And we're going to do it in terms of 6 divided by x when x is very, very close to 0, infinitesimally close to 0, right? So when x is close to 0, well, when numbers of x are less than 0, you can see the graph goes down, 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 and it keeps going down, down, down. So from the left-hand side, the y values get more and more and more negative, or closer and closer to negative infinity when x is closer and closer to 0. These are values of x which are smaller than 0. On the other side, when we choose values of x which are larger than 0, as we get closer and closer and closer to 0, remember our target value of x is 0, the y values go, well, off the screen, but I can zoom out a little bit. But you can also see that as I get values of x closer and closer and closer to 0 from the positive side, the y values get higher and higher and go to positive infinity. So 6 divided by x is some version of negative infinity or positive infinity, depending if you go from one side to the other side. Basically, we say it's undefined, but we could be smarter than this, right? We know this is not defined. So I'll say undefined, but something like plus or minus infinity might be a much more accurate and more sophisticated answer, right? Something like that, if we can look at it in this particular situation, as x is getting closer and closer to 0. And we can do x over 4. Again, we can analyze it by using x values that are closer and closer and closer to 0. So y equals x over 4. Let me turn off this other one. So we want to find out when x is closer and closer and closer to 0. That's our target number. And this function is continuous. Well, I guess, yeah, even at 0, it has a closed circle of 0, 0. Right? So everywhere it's continuous. Since we know it's continuous, we can just plug it in. But we also know the answer just by looking at the graph. When x is slightly larger than 0, the y values are getting closer and closer to 0. When x is smaller than 0, the y values are also getting closer and closer to 0. So 0 divided by 4, or the limit as x approaches 0 of x divided by 4, whether you look on the right side or whether you look on the left side, this is equal to 0. 4x minus 3x squared over x. If I try to plug in x equals 0 right in here, I have a 0 in the denominator. Again, not really sure how to calculate that, but we do know that we could simplify these things, right? We do know that algebraically, we can oftentimes simplify polynomials. And this one I made can be simplified. The top can be factored. X is a common factor. If I factor the top, it's x times 4 minus 3x. Remember, you should always double check that your factorization is correct by remultiplying. X times 4 is 4x. X times minus 3x is negative 3x squared. So I'm recovering this polynomial on the top by multiplying or distributing on the factored thing. So on the bottom, I just have my x, and the x's now divide. And so I'm left with the limit as x approaches 0 of 4 minus 3x, which now this is a continuous function. 4 minus 3x is just a linear function. So I can put in 0 here. And I get 4. So please be aware, if you have 0, don't be too afraid of it. This one, if you think of this problem a little bit more closely, you'll notice that when you plug in 0 in the denominator, you get 0. But when you plug in 0, you also get 0 in the numerator. This is an example of 0 divided by 0. 0 divided by 0 is not called undefined. It is called indeterminate because we need to do something to determine it. It could be 0, it could be undefined, or it could be 4 in this situation. But look out for 0 over 0. It is one of the cases that we study quite a bit because when it's not 0 over 0, when it's like 6 over 0, we know what the answer is. It's something like plus or minus infinity, but technically undefined. When it's 0 over 4, we know the answer is 0, but with 0 over 0, it can be lots of different things. And lastly, we have 6x over tangent 2x. If I try to plug in 0 directly, I get 6 times 0 on the top. And when I plug in 0 directly, I get tangent of 2 times 0. Remember, you can just plug in the 0 in the bottom. Now that looks like 20, so maybe I'll put another parentheses around here just to say it's 2 times 0. Okay, so the top here becomes 6 times 0, which is 0. The bottom becomes tangent of 2 times 0, which is the tangent of 0. So the tangent represents the slope at that particular angle for the point on the unit circle and the origin. So if I'm at 0, the slope is flat line, so the slope is equal to 0. So the tangent of 0 is equal to 0. So this is another example of an indeterminate form. I'll spell it right here. Indeterminate. And we would need to do more investigation to find out what's going on. So don't be afraid of 0. We could use some fancy formulas to help us simplify this. We don't know them yet because we haven't done chapter 3. So what I would do is I would put this into my calculator and use a table or a graph to try to figure out what 6x divided by tangent 2x was in this particular situation when x is very, very close to 0. I'm going to try that and see what you get. And you can always email me if you want to check your answer. Or if you have any other questions, please reach out. I hope you found this video helpful. And I also hope you have a nice day.